Okay, so the next thing that we have to learn about when we're looking at vectors and things like that, we've already in a previous video looked at finding a resultant vector. The next thing we need to be able to do is to break a vector up into its components. So if we have just a single vector acting in some direction, we should be able to break that up into kind of two component vectors in horizontal and vertical direction, we'll say. So imagine a situation where you have a problem that is talking about something like, a football being kicked. So you have a football here on the ground like this, and this is kicked off in a particular direction at maybe 30 degrees angle to the ground like this. And the idea is that you have to answer some sort of VUAST problem where you sort of say, let's look at the distance away, certain distance away. How long does it take to get, 30 meters or something away from the ball's initial position, just in the horizontal direction, right? So it doesn't really matter, how high up it goes. It's just how long it takes to get that distance away in the horizontal direction. Well, then you would need to look at, obviously this velocity, this initial velocity here, if we were to pick some sort of initial velocity like u is equal to 12 meters per second, like that, we might say something like, what's important here, if we're only dealing with the horizontal position, we couldn't say that it's traveling in this direction at 12 meters per second. It's not. It's traveling kind of up into the air. So what's the speed over the ground? Well, you'd have to break this vector up into its components. So what would that look like? Well, let's draw the vector out here on its own. So you would have your vector here with a length of 12 like that, and then you would have components in a particular direction. So here's one component, which is the horizontal component. You can see it's the kind of length on the ground, if you're to look directly down at it. And that has some particular length. And the other one is the height up from the ground, kind of like this. So you've got this vertical component like that, and that's the vertical component of your of this vector here, right? So we could call this these x and y. So we'll say that this is in the x direction because it's horizontal, and this is in the y direction. So let's, for now, if we were to call this u, this side here, u equal to 12, well then we could call this one x here, and we could call that one y. So we want to know, now obviously we have a 30-degree angle in here as well that we need to use in a second. Okay, so we want to know, well, what is the length here of x? So we need to use trigonometry for this. We've got our hypotenuse here again of 12 that we know. We've got an angle of 30 which we know, and we're interested in x here, which is the adjacent. So adjacent over hypotenuse would give you cos. So because we've got adjacent and hypotenuse, let's use that. Cos of 30 degrees, because that's the angle, is equal to the adjacent over the hypotenuse. So that is x over 12. Now that's cos 30. So I just want x on its own. I don't really care about the rest. So what I want to do is on this side, I need to multiply this side by 12 in order to get rid of this 12 on this side. But that means I have to multiply this side by 12 as well. So I'm going to just rearrange this, the right-hand side onto the left and the left-hand side onto the right. So I'll get x over 12 is equal to cos 30. And so if I multiply both sides by 12 now, I'll get x is equal to 12 times cos 30. Right. So what does that work out as? Well, 12 by cos 30 is 0.866 or something. So 12 by the cos of 30 degrees will give me, that gives me 10.39 we'd say meters per second, because that was initially a speed. So the speed over the ground then, if you kick this ball up at 30 degrees, at 30 degrees to the ground, and it had a speed of 12 meters per second in that direction. Well, if you were overhead looking straight down at the ball, it would just look like the ball was covering speed over the ground at this speed, 10.39 meters per second, right? Let's say we had to do a problem where we were looking at, well, this ball goes up, and so obviously there's an acceleration due to gravity, so it slows down, and then it comes back down again. So again, if you were over here looking at this ball, you would just see it go up in the air and back down again like that. So you would only care about the vertical direction here. So what would be the speed of this ball in the vertical direction as it was kicked off? Let's look at that. That's y in this diagram. It's this part of the vector. So y then is the height. We've got a 30-degree angle here, and we've got the hypotenuse. Y is the opposite for this angle of 30 degrees. So I've got opposite and hypotenuse, which is sine. Sine of 30 degrees here is equal to opposite, which is y, over the hypotenuse, which is 12. So I just want y on its own. So I have to multiply both sides by 12, and then I'm going to switch sides as well. So I end up with y is equal to 12 times sine of 30 degrees. And because I know that that's 0.5, y is equal to 12 times 0.5, so y is equal to 6 meters per second. So again, if you stand very far away from the ball being kicked over here, and you just look at it being kicked towards you, we'll say, you would just see the ball go up in the air like this and come back down again. And that would be as if somebody had just thrown something straight up in the air with a velocity of 6 meters per second, and it went straight up in the air and decelerated down to a velocity of 0 and then dropped back down. But that's how we break this up into different components. Now, if you imagine that these were forces or something, right? This y and x. If I took a vertical vector like this with a force of 6 newtons, we'll say, and if I took a horizontal force with magnitude of 10.39 newtons, and I combine those, well then my resultant vector would be this. It would be a vector of length 12 newtons, and it would have it would make an angle of 30 degrees with the horizontal. So what we've seen when we've worked out a resultant vector is the opposite of this. These are the opposite of each other. One is getting a resultant vector, so taking two vectors that are 90 degrees to each other and finding a result, an equivalent vector for that. And the other one is getting a vector that's already at some angle. It's almost like the resultant vector, and then working backwards to get the horizontal and vertical components that made up that vector to begin with. All right, that's it. Those are two simple examples at looking at, that's a simple example of finding the components of a vector as they're needed in a problem.